In this video, I'm going to talk about line regulation and load regulation. These are two very important parameters that are useful in characterizing the performance of voltage regulators. Let's start with line regulation. Line regulation allows us to quantify how good a power supply is at maintaining a constant voltage despite changes at the input side. We can express it as a percentage. It's just the ratio of change in the load voltage to a change in the line voltage. Smaller is better because you want the load voltage to just be constant, to not change at all, even though your line voltage might be fluctuating. Sometimes line voltage is also alternatively expressed in terms of a percentage per volt, where there's the load voltage down here in the denominator. Let me show you an example. Let's say that we have a 12-volt power supply at constant load, constant temperature, and it nominally provides us 12 volts with a particular input voltage, in this case 12.5 volts. However, we're told that when the input changes, the output also changes a little bit. Obviously, we would want this number to also be 12 volts. The fact that it's not 12 volts shows that the regulator is not perfect. The line regulation tells us how imperfect this particular voltage regulator is. Using the equation at the top, let's calculate the line regulation as a simple percentage. There's the change in the load voltage, and there's the change in the line voltage. Multiplying that ratio times 100, we find that the line regulation is 0.2%. That's a fairly typical value that you would find on a well-designed voltage regulator. Let's now express line regulation using the alternative definition that you'll sometimes see in data sheets. We get 0.016% per volt. This is also a fairly typical value for line regulation of a well-designed voltage regulator. Let's now look at load regulation. Load regulation expresses how good a power supply is at maintaining a particular constant voltage at the output side despite a changing load resistor. Let's make a simple plot of the load voltage versus the load current to illustrate what load regulation tells us. When there's no current flowing to a load, that is, when the load resistor is infinite, we have the no load case. That's V sub NL in this equation. If the regulator were perfect, then that voltage would be maintained no matter how much current we're drawing through the regulator. Of course, no voltage regulator is perfect, and we can expect the voltage to start to sag when we draw more current from it. The output voltage of the regulator, when we have the minimum specified resistance attached to it, is called the full load voltage. Remember, full load means smaller resistors. No load means very, very large or infinite resistors. Smaller resistors use more current. Ideally, there would be no difference between no load and full load, so the difference here in the numerator would just be 0. Let's look at an example and calculate the load regulation. Let's assume that a 12-volt power supply at a constant temperature gives us 12 volts when only a voltmeter is used. Now, if only a voltmeter is used, that means we don't have a resistor attached to it. Without a resistor, the load resistance is infinite, so this is the no load case. Let's indicate that here in our diagram. Then we're told that the voltage drops to 11.94 volts when the load was at its minimum according to the data sheet. So when the resistor is at its minimum value, we're getting 11.94 volts. We now have everything we need in order to calculate load regulation for this regulator. Using the equation above, we can just substitute in these two values. We find that the load regulation for this particular example is 0.5%. Again, this is a typical value for load regulation that you might find in a well-designed regulator.